Okay, so let's go ahead and take a look at this next lesson. So this lesson is about graphs of functions and derivatives, and it's all about review about graphs of functions and derivatives. So that means that everything we kind of did with the first derivative test, increasing, decreasing, critical numbers, concave up, concave down, points of inflection, that's all actually in this lesson. So remember Rolle's theorem, and there's a little illustration here. Rolle's theorem states that if f is continuous and differentiable, and if f of a is equal to f of b, and in this case they made it on the x-axis, then there's at least one number c in the interval such that the derivative is equal to 0, meaning that there's a horizontal tangent somewhere between a and b. Okay, and then mean value theorem, continuous, differentiable, then the equation of the tangent line is parallel to the secant line that connects both A and B together. So here's an illustration. Here's my tangent line, and then here's my secant line. Okay? So now let's look at example 1. If f of x equals x squared plus 4x minus 5, show that the hypothesis of the Rolle's theorem is satisfied on the interval, and find all the values of c such that it satisfies the conclusion of the theorem. Check all 3 conditions of the hypothesis of the Rolle's theorem. So that means we have to check continuity, differentiability, and also we have to check if f of a is equal to f of b. Okay. So first, this is a polynomial. So because it's a polynomial, it is continuous everywhere. And then it is differentiable because it's also a polynomial. So we have to check f of b and f of a being equal to each other. So f of negative 4 squared plus 4 times negative 4 minus 5. And remember, when I plug in like f of negative 4, if you want to use synthetic division to evaluate this, you're more than welcome to do it. And if you want to know about the synthetic division way, if you ask me, I can show you. Or I could probably just show you right after this if you were really curious. So what you get for both of these is you get, oh, this should be, no, they're both negative 5. Okay. So this is negative 5. And then you have 16 minus 16 and minus 5, which is also negative 5. Okay, but if I wanted to use synthetic division real quick, I plug in my negative 4. My coefficients are 1, 4, and negative 5. Bring down the 1, negative 4, 0, 0, so you get negative 5. And that is my f of negative 4. So you can always use synthetic division. So f of 0 is equal to f of negative 4. So now I want to find the derivative. F prime of x is equal to 2x plus 4. And I'm going to set this equal to 0. I wanted the value of c such that the derivative is equal to 0. So this is 2c plus 4. You don't have to like substitute the c in for x. It's proper mathematical notation, but I don't think College Board would take points off if you left it as x and solved. With proper notation for Rolle's theorem, you would have plugged in c in for your x. So 2c plus 4, subtract 4 from both sides, so negative 4 is equal to 2c, so c is equal to negative 2. Okay, so let's take a look. Let f of x be equal to this function. Using Rolle's theorem, show that there exists a number c in the domain of f such that f prime of c is equal to 0. Find all the values of c. Okay, so what you're going to want to do is you're going to want to look to see whether or not it's continuous and differentiable everywhere. And then you want to calculate the zeros. So I think we can probably use Desmos. Or you can use your graphing calculator. So f of x, f of x equals x cubed divided by 3 minus x squared divided by 2, and then minus 2x and plus 2. Okay, so here's my graph. And what I'm saying is that somewhere in the domain. So that means that in order for me to satisfy Rolle's theorem, I'm going to have to figure out what these values are. So negative 2.3 and 0.9 and also 2.9. So that means that those are my x-intercepts, which means that somewhere in between all those numbers, I have a c such that the derivative is equal to 0. So going back here, f of x is continuous and differentiable because it is a polynomial. I shouldn't abbreviate. So by graphing, and if you can't use your graphing calculator, then you're going to want to try to factor. And in this case, because it's a cubic and it doesn't factor by grouping, then you're going to probably want to use the rational root theorem, which is something that we did in advanced math. So at x is equal to negative 2.3, and at x is equal to 0.9, and at x is equal to 2.9, you have zeros of the function, which means that f of negative 2.3 is equal to f of 0.9, which is equal to f of 2.9. And because those are all equal to each other, then somewhere between negative 2.3 and 0.9, and also between 0.9 and 2.9, you have somewhere where the derivative is equal to 0. So we'll go ahead and find the derivative. F prime of x, x squared minus x minus 2. And I'm going to set this equal to 0, but I'm going to plug in my c first just to be mathematically correct. And then I'll set it equal to 0. C squared minus c minus 2. And then I can do my little diamond if I need to. So negative 1 and negative 2. Negative 2 and positive 1. So 0 is equal to c minus 2. And c plus 1. So c is negative 1 and 2. Which negative 1 lies between my negative 2.3 and 0.9. And my 2 lies between 0.9 and 2.9. Okay, so example 3. The points P is 1, 1, and Q is 3, 27 are on the curve f of x is equal to x cubed. Using the mean value theorem, find the value of c in the interval 1, 3 such that f prime of c is equal to the slope of the secant at PQ. So I need to figure out what the slope is of PQ. So that's 27 minus 1 divided by 3 minus 1. So I get 26 over 2, which is 13. And now f is continuous and differentiable because it is a polynomial. So then I'm going to find f prime of x, which is equal to 3x squared. To be mathematically correct, I'm going to substitute c in for my x. So 3c squared is equal to 13. And then I'm going to solve. So divide both sides by 3, so 13 over 3. Square root both sides, so c is equal to plus or minus the square root of 13 over 3. Now, the negative value does not exist between 1 and 3. So your only value of c is the positive one. C is equal to negative root 13 over 3 is not in the interval from 1 to 3. Okay? So now, let's move to example 4 here. Let f be the function f of x is equal to x minus 1 to the 2/3 power. Determine if the hypothesis of the mean value theorem is satisfied on the interval, and if so, find all the values of c that satisfy the conclusion. Okay, so between 0 and 2, I'm going to go ahead and I'm going to use Desmos to graph. And if you didn't know that it was not differentiable somewhere, you'd have to use Desmos to graph. Let me give you a little trick, though. Whenever you have a fractional exponent, you have a cusp. Where you have that cusp is the value of x when you take what's in the parentheses and set it equal to 0. So at x equals 1 is a cusp, which is a non-differentiable point. And if you're a little skeptical, let's use Desmos again. So I have x minus 1 to the 2 divided by 3 power. And what you notice is that that value right there is a cusp, just by looking at the graph. Which means that this does not satisfy the hypothesis of the mean value theorem. So, since x equals 1 is in the interval 0, 2, then there doesn't or does not exist a value c such that f prime of c is equal to f of b minus f of a over b minus a by the mean value theorem. Okay. So now, do some more things with the calculator. In your homework, if I'm allowing you to use the calculator, it will say something like calculator OK, and then you know you are allowed to use your calculator. You can use your calculator. If it says nothing, then you're to assume that you're not allowed to use your calculator for it. Extreme value theorem states that if f of x is continuous in the closed interval, that you have a minimum and a maximum value on the interval. It is like your absolute min and absolute max. Okay, so let's go ahead. I'm going to use the calculator for a couple of these just so that you guys can see how you can use your calculator to do these. Okay, back when we did this originally, you found the critical numbers and then you tested the endpoints, and whichever one had the largest y value or the most positive y value was the maximum, and then the smallest y value or the most negative y value was your minimum value. Okay, so let's go ahead and use the graphing calculator here. I'm going to just double check and make sure that all my plots are off so my graph doesn't come out weird. Okay, so I'm going to go y equals, and I already have some functions in here, so let's clear those out. So now let's look here. I want to do x cubed and then plus 3x squared and minus 1. And now I can set my window to be between -2 and 2. So let's do that. So let's go -2.5 to 2.5. And let's go like -20 to 20. just because it's a cubic and I just want to make sure that we get everything in the window. Okay, so now we hit graph. So my smallest y value is going to be something like that's over here. Over at like negative 1. So let's trace here. So that's probably like my my smallest value is probably not -1 on the x, but looks like -1 on the y. So my y-intercept is my lowest y value on the interval. So this is just strictly on the interval closed between -2 and +2. And then looks like my largest y value is going to be whenever x is equal to 2. So, oops, wrong thing. And so what I just said, my largest y value is going to be when at the end of the interval, which is going to be when x is equal to 2. So that's 19. So that means that based upon my graph, my maximum value is going to be positive 19. And my minimum value is going to be -1. And this corresponds at x is equal to 2, and this corresponds to x is equal to 0. So your minimum or your maximum could occur at an endpoint, or it could occur at a critical number. And in this case, my minimum occurs at a critical number. Okay. So now if I look at example 6, let's graph this one again as well. So y equals, clear this function out. So 1 divided by, what is it, x squared. And just so it doesn't get a little strange, let's make sure that our x squared is in parentheses. Okay, so now we're going to hit graph. And I'm on the interval from 0 to 3, so now I can change my window. Let's go -0.5 to just a little bit bigger than 3. So I have this part of my parabola. So by using your calculator, you'll notice that the graph goes towards positive infinity, and because x cannot be equal to 0, because it gives you 0 in the denominator, there is no maximum value. But the minimum value can occur where my x is equal to 3. So, and this is basically just looking at the graph. And when x is equal to 3, I'm at 0.11111 repeating, which is actually the equivalent fraction of 1/9. Okay. So there's no maximum value. But your minimum value is 1/9 on this particular interval. Okay? So now let's take a look. Definition of a critical number. Critical numbers are where the derivative is equal to 0 or any non-differentiable points. Function is increasing, function is decreasing. You'll use the derivative to tell you that. So when the derivative is bigger than 0, it's increasing. When the derivative is less than 0, the original function is decreasing. And there's some graphs here if you want to take a look. So example 7 is to find critical numbers. So I'm going to take my derivative. So f prime of x is equal to 12x squared plus 4x, set it equal to 0. 12x squared plus 4x. Factor out of 4x, so you're left with 3x plus 1. So x is equal to 0 and negative 1/3. So those are your critical numbers. Again, take another critical number, take the derivative, f prime of x, 2/5, x minus 3 to the negative 3/5 power. That as a positive exponent looks like 2 divided by 5, x minus 3 to the positive 3/5 power. Derivative equal to 0 is when the numerator is equal to 0, provided that there's x. Where it's non-differentiable is where the denominator is equal to 0. So the denominator is equal to 0 when x is equal to 3. And that's my non-differentiable point. So now let's take a look at the graph where the function is increasing and decreasing based upon the graph. So my derivative being bigger than 0, I should change colors. So my derivative being bigger than 0 is here. So that means that on 2, 5, f of x is increasing. And then where f prime of x is less than 0, which is on negative infinity to 2 union 5 to positive, oh, I'm sorry. It's not negative infinity. And positive infinity, it's 1 to 6. So from 1 to 2 and from 5 to 6, you will get f of x being decreasing. Okay, so let's take a look at your next one. So we have to do the chart for the next one. When you do the chart, you are going to first need to take the derivative. So f prime of x, 2/3, x squared minus 9 to the negative 1/3 power times the derivative of the inside because it's chain rule. So 2x. So f prime of x is 4x in the numerator, 3 times x squared minus 9 to the negative 1/3 in the denominator. That means you set your 4x equal to 0, so x is 0. And you set your denominator equal to 0, so 3 times x squared minus 9 to the negative 1/3 is equal to 0. So you get x squared minus 9 to the negative equals 0. Take the negative cube root of, or negative cube at both sides, so x squared minus 9 is still equal to 0. So x is plus or minus 3. So that means negative infinity to negative 3, negative 3 to 0, 0 to 3, and 3 to infinity. Pick test values, so x equals negative 4. I don't know why I would use 5. I used 5 on my notes. Negative 4. X equals negative 1, x equals positive 1, and x is equal to 4. F prime of negative 4, when I plug it into my equation, I get less than 0. f prime of -1, I get bigger than 0, f prime of 1, and I get less than 0, and f prime of 4, and I get bigger than 0. So conclusion of f of x is decreasing, increasing, decreasing, increasing. So f of x is decreasing on negative infinity to -3, union 0 to 3. And f of x is increasing on -3 to 0, union 3 to positive infinity. Okay? So we're going to use a calculator for example 11. I want to see where the function is actually increasing. So I want to plot cosine of x squared, and I want to plot between negative pi divided by 2 and positive pi over 2, which I plug it in directly as pi, and then your calculator will automatically adjust. And now because of the way sine and cosine operate, we can look at it this way. So I want to know by looking at my function here where f is increasing. Okay, now let's be clear. This is f prime is equal to cosine of x squared. So what I just graphed here was my graph of my derivative. So that means that it's increasing between both of these little x-intercepts. So if we trace, and we could actually calculate the exact one. So go second calc and go 0. Left bound is left of the x-intercept, right bound is right of the x-intercept. So I get negative 1.25331. I could do the exact same thing on the other side because sine and cosine are periodic. It's the positive side here, so it's positive 1.253314. So if we take a look at so now we could say that f of x is increasing from negative 1.25331 to positive 1.25331. Okay? First derivative test tests whether or not you have a relative min or a relative max, or neither one. Take the derivative. If the function goes from decreasing to increasing, you have a minimum. Increasing to decreasing, you have a maximum. If it doesn't change sign, then you don't have neither. And some more little graphs here. Second derivative test also tests maxes and mins, but it uses a second derivative. If the second derivative is bigger than 0, that means the function is concave up, so you have a relative minimum. And then the second derivative being less than 0 means the function is concave down, so you have a relative max. So they're kind of sort of like backwards in a sense, but if you draw it and you think about concavity, then it makes more sense. So here's the graph. I want to show where I have my relative extremis, so my relative min and my relative max. So what you notice is that I am increasing, or I just drew it in green, where f prime is bigger than 0. And I'm decreasing for my original function f, where my f prime is less than 0. So where I change from increasing to decreasing is a relative maximum. So at x is equal to -2, f of x has a relative max because, f of x goes from increasing to decreasing. And then at 3, f of x has a relative min because f of x goes from decreasing to increasing. Okay? So now we'll take a look at another example problem. Find the relative extrema of this function. I first need to find the derivative. So f prime of x is equal to x squared minus 2x minus 3. Set it equal to 0 and factor. So x minus 3 and x plus 1. So your critical numbers are -1 and 3. You can use the first derivative test by doing the chart and seeing where it increases and decreases, but since we've kind of already have done the chart once, let's use the second derivative test. Second derivative test would say to find the second derivative. So that's 2x minus 2. And then we're going to plug in my critical numbers, -1. So 2 times -1 minus 2 gives me -4. And f double prime of 3 is 2 times 3 minus 2. So 6 minus 2, which is +4. By the second derivative test, this is concave down, and that's concave up. So by the second derivative test, x equals -1 is a relative maximum, and x equals +3 is a relative minimum. You will probably need to find the corresponding y values. So anytime they ask you an open-ended question like this, you should find the corresponding y values. So f of -1. So -1 cubed over 3 minus -1 squared minus 3 times -1. So you'll get 5/3, and then f of 3 cubed over 3 minus 3 times minus 3 squared minus 3 times 3. So you'll get -9. So really, to be like clear, you should have probably have put -1 comma 5/3 here, and then 3 comma -9 there. Okay, Find the relative extremity of this function. We've done this derivative already once before. F prime of x, 2/3 x squared minus 1 to the 2/3 times 2x. So f prime of x, 4x. It's not 2/3 here. Negative 1/3. X squared minus 1 to the positive 1/3. So you set both things equal to 0. So you get 0. 3x squared minus 1 to the 1/3 power is equal to 0. So x squared minus 1 to the 1/3 power is still 0 because when you divide both sides by 3, you still get 0. When you cube both sides, you still get 0. So x squared minus 1 is equal to 0. So x is plus or minus 1. So negative infinity to negative 1. Negative 1 to 0. Might be a little bit easier. I guess it doesn't matter. 0, 1, and 1 to infinity. The reason why there's these extra boxes here is because I thought it might be easier for you to classify your x is equal to negative 1 and x is equal to positive 1. So if you wanted to, you could actually change this to be like x is equal to negative 1 here, and then go from negative 1 to 0, x equals 0, go from 0 to 1, x equals 1, and then go from 1 to infinity. It's up to you how you really want to do it, but, you know, if this confuses you because you have too many boxes, then you can do it the way we always used to do it. So x equals negative 2. So f prime of negative 2 is less than 0. So decreasing. Here it doesn't exist. Here at negative 1 to 0, so x equals negative 1/2. F prime of negative 1/2 is going to be bigger than 0, so this is increasing, which makes this a relative minimum. And then x equals positive 1/2, so f prime of 1/2 is less than 0, so this is decreasing, which makes this the relative maximum. And then x is equal to 2, so f prime of 2 is bigger than 0, so this makes it increasing. So this makes it a relative minimum. So by the first derivative test, so let's find out what x equals. So f of negative 1 is negative 1 squared minus 1 to the 2/3 power. And then f of 1 is 1 squared minus 1 to the 2/3 power. So both of these are actually 0. So negative 1, 0, and 1, 0 are relative minimums because f of x goes from decreasing to increasing. And then what happens at x equals 0? F of 0 is 0 squared minus 1 to the 2/3 power, which gives me positive 1. So, and 0, 1 is a relative maximum because f of x goes from increasing to decreasing. So the next thing that we're going to talk about is concavity or concavity. Function is concave up when it holds water. Function is concave down when it doesn't hold water. Double prime bigger than 0 is concave up. Double prime less than 0 is concave down. Points of inflection is when it changes from concave up to concave down, or concave down to concave up. And there's a lot of illustrations here about it. So let's take a look at example 15. I want to find all the points of inflection and determine where the function is concave up or concave down. So and the interval should be -3 to 5, not +3 to 5. Okay, so from -3 to 5 on this interval, I want to know where it's concave up. Remember with graph interpretation, where my derivative is increasing has positive tangent lines. So that means on -3 to 0 and 3 to 5, f of x is concave up. And then where I have decreasing, so negative slopes of the tangent lines, if I were to draw many tangent lines all the way through, so from 0 to 3, f of x is concave down. And then my points of inflection are where it changes from concave up to concave down. So at x is equal to 0 and x is equal to 3, f of x has points of inflection. (16) is find all the points of inflection and determine where it's concave up and concave down. So before we can find a double prime, we have to find a prime. So this is 3x squared minus 12x plus 12, and then we'll take a second derivative. So that's 6x minus 12, and then you're going to set it equal to 0. So when you set it equal to 0, 6x minus 12, so 12 is equal to 6x, so x is equal to 2. So you have your interval, test value, sign of f double prime, and then conclusion, and this conclusion is always about the original function, unless stated otherwise. So unless you're trying to find like the maximum of the derivative, for example, that's the only way you're gonna change what the conclusion is about. So -infinity to 2, and then 2 to positive infinity. So pick x equals 0, pick x equals, I don't know why we pick 5. Pick x equals 3. F double prime of 0 is going to be less than 0, and f double prime of 3 is going to be bigger than 0. So f of x is concave down, and f of x is concave up. So then you'd find your f of 2, scroll down too much, f of 2 is 2q minus 6 times 2 squared plus 12 times 2 minus 8. So you get f of 2 is equal to 0. So f of x is concave down on -infinity to 2. F of x is concave up on 2 to infinity. And then f of x has a point of inflection at 2, 0. Okay, so let's take a look at example 17. So 17, I want to find out the points of inflection and figure out where it's concave up and concave down. Okay, so take a derivative, f prime of x 2/3 x minus 1 to the negative 1/3. Take another derivative. So you get negative 2/9 x minus 1 to the negative 4/3 power. So then you're going to set this equal to 0. So you're going to get x is equal to 1. So then I do interval, test value, sine of f double prime of x, and conclusion of f. So now what I'm going to do is I'm going to negative infinity to 1, and then I'm going to go from 1 to infinity. So I'm going to set up my table. So test value 0 and 2. What you find is f double prime is less than 0, and f double prime is also less than 0. So this is concave down and concave down. Means that there's no points of inflection. And f of x is concave down from negative infinity to 1, union from 1 to infinity, with parentheses. You have to separate it up. You can't go from negative infinity to positive infinity, because at x is equal to 1, the second derivative is equal to 0. Okay, so now this is a multiple choice question. The graph of f is shown in the figure below. F is twice differentiable. Which one is true? So this is the graph of f. So at 5, f of 5 is equal to 0. F prime of 5, this function is decreasing. So f prime of 5 is less than 0. And then this function is concave up. So that means that f double prime of 5 is bigger than 0. And so which one works? Letter C. So 19. We only have 2 more left. So given the graph below, I want to find all this stuff. So relative mins and relative maxes, increasing and decreasing, which I'm going to have to find increasing and decreasing before I find relative mins and relative maxes. So let's do part B first. So it's increasing when f prime is bigger than 0. So that goes from negative infinity to negative 4, union from 0 to 4. And then it's decreasing where it's below the x-axis. So f of x is decreasing on negative 4 to 0, union 4 to positive infinity. And then I want to find my relative mins and my relative maxes. So part A, at x is equal to negative 4 is a relative maximum. And at x is equal to positive 4 is a relative maximum as well. And at x is equal to 0 is a relative minimum. Because it says nothing about justifying your answer, I can just write out my answers. When in doubt, justify your answers. So this would have been because f of x goes from increasing to decreasing. And this would have been because f of x goes from decreasing to increasing. Justifying your answer is equivalent to like showing your work. Okay, so now points of inflection. change colors, where it changes from concave up to concave down. So we probably have to find D first. So the function is concave down here and there. So we'll find D first. So f of x is concave down on negative infinity to negative 2 union 2 to positive infinity. And then change colors again. Concave up here. So f of x is concave up on negative 2 to 2, which makes C, f of x, has points of inflection at x is equal to negative 2 and 2, because it changes concavity. Example E says to try to graph a sketch a graph. So negative 4, positive 4, should have had some relative maxes here. At 0, probably would have had a relative minimum. Here would have been your points of inflection. So you're looking probably something like this for your graph. Okay. Last one. Figure out where my horizontal tangents are. Horizontal tangents are here, where I have possible relative mins and relative, oops, nope, sorry, they're not there. Possible relative mins and relative maxes, which are at my zeros of my f prime. So for A, x equals negative 4, 2, 4, and 8 are my horizontal tangents. So my relative extrema increasing, 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 decreasing, and decreasing. So at x equals negative 4 and x is equal to 4, f has relative max. And at x is equal to 2 and x is equal to 8, f has relative minimums. And I already answered C, kind of. So f of x is increasing on negative infinity to negative 4 union 2 to 4 union 8 to infinity, and f of x is decreasing on negative 4 to 2 union 4 to 8. Okay? And then D, where you have points of inflection, so let's do concave up and concave down first. Concave down, and then let's go concave up and concave up. So let's answer E first. F of x is concave up on negative 1 to 3 union 6 to infinity, and f of x is concave down on negative infinity to negative 1 union 3 to 6. So that makes my point of inflections for D. F of x has points of inflection at x equals negative 1, 3, and 6, because I change concavity. And that is it for this lesson.